Hello everyone, today we're going to look at minimum and maximum problems. So recall that minimums and maximums are types of critical points, and those are the x values for which the derivative is 0 or undefined. More likely than not, though, we're going to be looking at when the derivative is 0 versus being undefined. So for our first example, the height of a ball thrown upwards in meters after t seconds is given by s of t equals 64t minus 16t squared plus 6. What is the highest the ball goes? So the highest is the same as what is the maximum. So we want to find the maximum, which means we need to find the critical points. So we're going to take the derivative, so s prime of t is 64 minus 32t, and we set it equal to 0. Then we solve for t, and hopefully we can see that it's 2 seconds. So now we go back to what is the question asking. If the question was, at what time does the ball hit its highest point, then our answer would be 2 seconds. But the question is, what is the highest the ball goes? So the highest is the position, is the meters, so I want the value of the function itself, not just t. So to answer the question, I'm going to plug 2 into my function. So s of 2, hopefully you'll get out 70, right? So every t becomes a 2, plug it in, and you should be getting 70. The units are meters, right? So the highest the ball goes is 70 meters. Now notice we didn't actually decide if this critical point was a maximum, but because there's only one critical point, it's going to be the one we want. So if there's more than one critical point, then we have to decide which is the one that we want. But if there's only one, it's going to be the one that we want. So let's try another one. A manufacturer needs to make a cylindrical can that will measure 2 feet cubed. Determine the dimensions of the can that will minimize the amount of material used in its construction. So we want to minimize the amount of material. So we're going to have a couple of things to look at here. First is the volume. I know that the volume is going to be 2 feet cubed. And then we also need, again, the amount of material being used. So the volume is 2, and then the amount of material is the surface area. So I'm going to use SA for surface area. So if I think of a cylindrical can, something like this, we have the top and the bottom, and those are my 2 pi r squared. So remember, the area of a circle is pi r squared, and we have 2 of them, the top and the bottom. And then this 2 pi rh is the side of our can. So what I do is I'm going to kind of unroll it, and if I unroll the side, I'm going to get a rectangle. The height is the height of the cylinder, which we call h, and the length is the distance around the circle, which is the circumference, which is 2 pi r. So that's how we're getting 2 pi rh as the surface area around the can, and then again the top and the bottom. Don't worry about having to come up with the equations. If it's not a really, really simple one, I will give it to you. So in this, I would give you the surface area equation. So what I do is I solve my volume equation for h, and I'm going to plug that in for h over here. So whenever you end up with 2 equations, you're going to take one of them, the one that has the number associated with it. That's called the constraint. So the number being 2 here. I solve the constraint for one of my variables, and I plug it into the equation that we're minimizing or maximizing. So plugging that in and simplifying, I have SA equals 2 over r plus pi r squared. So to differentiate it, I'm going to have to change my 2 over r so that it's in, something times r to a power. And that 4 should be an r. I'm not sure where that 4 came from. That should be an r. Okay, and then we differentiate. So 2 pi r to the 2r to the negative 1 becomes negative 4r to the negative 2. Again, that random 4 should be an r. and I'll differentiate that, and we get 4 pi r. I'm going to set it equal to 0 because I want the critical points. So r to the negative 2 will equal pi r. I'm going to cancel the 4's and bring this guy over. Okay, so r to the negative 2 equals pi r. Then I'm going to multiply both sides by r because remember, r to the negative 2 is 1 over r squared. Whenever what we want is in the denominator, we have to multiply it over. So I'm going to multiply both sides by r squared. And then to get r, I'm going to divide by pi and cube root it. So notice that if r is 0, then my derivative is undefined. It's a terrible undefined. So r equals 0 really is a critical point. It's where the derivative is undefined. But if r is 0, I don't have a can. So I know that that's not going to be the critical point I want. Right? R can't be 0. So it is a critical point, but I don't want it. So this is the one that I want. The question says determine the dimensions of the can. That means I need r and h. So r is roughly 0.683 units are feet. Right? The volume is feet squared, so the radius must be feet. And then I also need to find h. So I'm going to plug it back into my equation for h. And I'm going to plug in the whole r, not the rounded one. I want to be as precise as I can. So I'm going to use the whole original r. And I get roughly 1.366 feet. Okay, so those would be my dimensions. That would be the answer to the question. Let's try another one. An open box is to be made from a square piece of paper, 10 inches by 10 inches. We'll cut a square from each corner and fold the sides up. Find the dimensions of the box with the largest volume. So the dimensions, that means I want width, height, and length. So I'm going to have 3 numbers as my answer because there are 3 dimensions in volume. So I know volume, again, is length by width by height. And then I got to figure out how I'm going to put things in for L, W, and H because I can't differentiate it the way that it is. So I have a square piece of paper, and it is 10 by 10. So whenever you can, whenever it's something geometric, you should always try to draw it out. Then we're going to cut a square from each corner. And then hopefully you can imagine folding those sides up. Okay? So this square that I cut out, that's going to determine the volume. So that's my variable, that's my unknown. How big of a square should I cut out? So it's a square, so I know both sides are going to be the same. So I'll call it x. So each square is x by x. And when I fold it up, that's going to be the height. So I know the height is x. Now the question is, what's the width? So if I'm going to call this guy the width, it was 10, but now I've cut out x over here, and I've cut out x over here. So it was 10, but I'm subtracting 2 of my squares, so I'm subtracting 2x. The same thing is true with my length. It was 10, but then I'm taking out 2 lengths of x. Okay, so I have my height, I have my width, I have my length, and I'm going to plug those into my equation. Okay, then I'm going to multiply it out. So 100x minus 40x squared plus 4x cubed. And now this is the thing that I'm trying to maximize because I want the largest volume, which means I'm going to take the derivative, set it equal to 0, and solve. So the derivative, 100 minus 80x plus 12x squared equals 0. First thing I'm going to do is notice that 100, 80, and 12 all share a common factor of 4. So I'm going to divide everything by 4. So 25 minus 20x plus 3x squared equals 0. I have a quadratic. And again, when it comes to solving a quadratic, you can either factor it if it's factorable, or you can use the quadratic formula. So this guy is factorable, so I'm going to factor it. Remember, I want two numbers whose product is 75, a times c, and whose sum is the middle, negative 20. So there aren't that many factors of 75, and hopefully we can see that it is negative 5 and negative 15. Okay, so negative 5 times negative 15 is 75, negative 5 plus negative 15 is negative 20. So using those, I'm going to write it up over here. I'm going to separate my negative 20x into those two. Running out of room. And then factor by grouping. I have a 5 here. I take it out. I'm left with 5 minus 3x. My other half, I'm going to take out a negative a negative x rather. And then I'm left with 5 minus 3x. Assuming I have the same thing in my parentheses, which I do, 5 minus 3x, that means I've done it correctly. I can factor that out, and I'm left with whatever is not underlined, which I've now underlined twice. So I get 5 minus x times 5 minus 3x equals 0. Remember, something times something equals 0. One of those somethings must be 0. So either 5 minus x is 0, which means x is 5, or rather 5 minus 3x is 0, if I write it correctly, which means x is 5/3. So here's another example where I have two critical points, and I have to determine which of those is actually the maximum. So there's a couple of ways that I could do it. I could do the first derivative test, or since there's only two numbers and I want to know which one's going to give me the bigger one, I can just plug them both into the volume and figure out which one's bigger. If I plug in 5, 10 minus 2 times 5 is 0, and that's going to go away. So if x is 5, I don't have a box, because notice that's telling me that my squares are just going to cut my piece of paper in half. I'm not going to have any sides left to pull up. So it can't be 5, which means it has to be 5/3. Okay. But again, the question is find the dimensions. So I know one dimension is 5/3, and then I have to plug it in to find the other ones. So 10 minus 2 times 5/3 is going to give me 20/3. And remember, the height and width are the same because it's a square. So I'm going to have 5/3 by 20/3 by 20/3. And of course I wrote 10/3 there. X is 5/3. Okay. Pay close attention to this one. It's a really popular problem, hint hint. You want to make sure that you know what's going on. But let's look at another one. The sum of two numbers is 50. Find the two numbers if we wish to maximize their product. So we've got two numbers, which means I have two unknowns, which means I need two variables. I'll call them x and y. So the sum of two numbers means I'm going to add them. So x plus y is 50. I want to find the two numbers to maximize their product. So I need their product, which is x times y. So again, here I have two unknowns. I have two equations, one of which involves a number, and again, that's called the constraint. So I'm going to take the constraint, solve it for one of my variables, doesn't matter which one, and plug it into the product, which again is the equation I'm trying to maximize or minimize. So x equals 50 minus y. So P equals 50 minus y times y. And again, I'll distribute it, so 50y minus y squared. So this is the equation I'm trying to maximize. So again, that means I want the critical points. So I differentiate it, set it equal to 0, and solve. So hopefully we can see that y equals 25. I'm halfway done. I found one of the numbers. It says find the two numbers. So next, I'm going to plug y equals 25 into the equation that's already x equals. So x equals 50 minus 25, which is also 25. So both x and y are 25 in this case. Let's look at our last one. We want to fence in a rectangular area against a barn. So assuming the barn is long enough, what is the maximum area we can create out of 250 feet of fencing? So again, this is a geometry type problem, so we should always draw it out. So we have a barn. I'll call it B for barn. That kind of looks like a heart. It's supposed to be B. And then we're going to create a rectangular area against it. So I need two dimensions. I'll call them x and y. So maximize the area. So area is x times y. And we want to know how much we can create out of 250 feet of fencing. So the fencing is this, which is x, plus this, which is y, plus this, which is x. So my fencing is 2 x's plus a y. Now I have a lot of people who later will use this equation for the perimeter of a rectangle. But remember, a rectangle has 4 sides. This, I don't need the 4th side because the barn is part of it. So this only has 3 sides because of that barn. But in general, remember the perimeter of a rectangle has 4 sides, 2 x's and 2 y's. So please don't get this confused with the perimeter around an object. Okay. And then what we're going to do is we're going to take our constraint and solve it for one of our variables. And then we'll take that equation for y, plug it into area. So x times y, which is now 250 minus 2x. Distribute. So again, area is the equation we're trying to maximize. So we're going to differentiate it, where we get 250 minus 4x, set it equal to 0, and solve for x. And hopefully everyone should be getting 62.5 feet. Next, we're going to plug it into y. So y equals 250 minus 2 times 62.5, and we get 125 feet. The question is asking for the area. So area is x times y. We plug in our x, we plug in our y, and we get 7,812.5 feet squared. Okay. So try them out. Make sure that you're answering the question asked. So which of the variables are you actually solving for? And let me know if you have any questions. Thanks.